Okay, well, hey, welcome to another fun-filled day of physics. The plan today is to keep talking about diffraction. I introduced you to the idea, kind of talked about why it must be that we get that kind of interference pattern even with one slit. But we'll talk a little bit more about that. We'll talk about how um, that, along with double slit interference, showed you guys what you were seeing in lab 2 weeks ago, and then we'll also talk about how that plays a role in being able to resolve, to actually be able to discern individual objects, individual pictures, individual things. Why you have to be close enough to be able to see, for example, two distinct trees as opposed to the trees kind of forming one blob. It all kind of goes together. So that's the plan on my end. Um, but I'm just curious if there are any questions you guys have on any of the homeworks or anything. Hopefully you saw that I made the chapter 3 homework due Thursday. Um, since I didn't get it posted until last Thursday, I want to make sure you still had a full week. But let me just turn it over to you guys. Any questions about what we've been talking about so far? And I see Bradley's here now. Hi, Bradley.
Hello. I have a quick question.
Sure.
In words, what is the difference between interference and diffraction?
Okay, so they're very related, obviously, right? Diffraction we tend to reserve for the pattern that we see when we just go through one slit. Interference, we think of interference as having two distinct sources. And when we've looked at it, we've looked at it as like the two slits, so the sources from the two slits. Or if we want to talk about like thin film interference, the two sources are the two reflections, right? Where refraction, there aren't multiple sources. There's just the one source. It's just passing through, one one slit, one entry, one opening. But because of the wave nature of light, it still causes interaction between the individual wave fronts formed by Huygens principle. So I think that's how I would answer it. I would say interference, you need to have multiple sources, and the diffraction is just one, um, due to one opening.
Okay, sounds good.
So, because like you're not going to get diffraction if there isn't some sort of an opening that it's passing through,
Yeah.
right? Like if I shine a light here, and let's even make it monochromatic so we don't have to worry about that. So I'm shining a laser. That laser isn't going to create any kind of a pattern of bright dark or anything like that unless it's forced to go through some little opening. However, I can create interference without going through any kind of a anything, right? Like I could now have two lights that are pointed at the same spot, and if I've got them so that they're showing up exactly out of phase, for example, then they're going to cancel each other out and we're not going to see anything.
And showing up out of phase like that with a monochromatic, laser pointer, it depends on the geometry at which they were placed, correct?
Yes, and whether or not they started in phase or right, like, because we always sort when we set things up, we always start them off as they're coming in phase, right? That they're like in that double slit experiment. The double slit experiment, they have to be in phase because the light's hitting those two slits I mean, the same light, the same wave is hitting those two slits. So they are necessarily in phase. And then it's like you're saying, the geometry. It's okay, we look at the difference in the distances traveled. And if that difference in distances is some off by some half number of wavelength, we're going to get a dark spot. If it's off by some multiple of the wavelength, then we're going to get the bright spot. And then everywhere else, we get something in between. Um, and then with reflections, again, they're either in phase or they're exactly halfway out of phase, depending on which what kind of reflection we're getting. But again, it comes to the geometry, right? How much extra distance does the one travel as it's going through the film? But in general, just the interference, if I've got 2-point sources of light, the they may not be in phase at the start. They may not be exactly half a wavelength out of phase, right? But if I were to know where they are in terms of their relationship and their phase, then I'd be looking again at the difference in the distances, the geometry, as you said, and look for when do we meet up so that they are half a wavelength out of phase? When do they come together exactly in phase and the like? So I think that's a very long-winded answer to your question, but hopefully it covered what you wanted.
Sure did. Thank you.
Okay, you're welcome. All right, any other questions? So I got a question for you. Did you go around looking at light like this? Like, I'll just tell you right now, I can see the black lines between my fingers just looking at the computer screen.
I definitely did.
Yeah, were you able to see the lines?
Yes, like horizontal dim black lines.
Yeah,
Yeah.
it kind of looks like there's hairs,
Yeah.
or little strands of string or something in between your fingers. Yeah, they should be parallel to gap in your fingers. So if you've got your fingers like this, they should be horizontal, right? If you look this way, they should be vertical. That way they should be at an angle, but they should always be parallel to your little tiny strip. So anyway. All right, cool. Well, so that's diffraction, and it definitely happens. And if you go back and you look at what we talked about last time, you saw that the reason you get that is that you get like a series of waves. You can break up the entire region into pairs of waves that all end up canceling each other out. And so like we looked at those that were separated by half of the slit distance. And so like the bottom one in the middle cancel, and then the next ones cancel, and they all cancel the same spot. And so we get a dark spot. And then if you split it into groups of 4, so you're going 1/4 the distance, you see the same thing, and you go to 1/8, 1/6, 1/8, and so on. So what we end up with then, let me go ahead and share my screen here. There was the formula. Hopefully you guys can all see my whiteboard here. But there was the formula for the location of these dark spots, the destructive interference. And let me go ahead and write it up here. We found that we got destructive, so dark spots, when d sine theta equals m lambda. I'm going to use the book numbers, letters, whatnot. So what all those different things are, the d, that's the width of the slit. So let me go ahead and draw a picture of the slit here. So we've got this thing right here. So d was the width of the slit. The sine of theta, well, the theta is going to be if over here is our screen, and we've got our dark spot. There's our theta. And then again, lambda is our wavelength, and then m is just the regularness of this. And you can change this using the small angle approximation. So another way we saw this was you can write it as d theta equals m lambda. You can also turn it into d tangent of theta equals m lambda. And I think I called these guys x and l, which allows us to turn this into a formula with the linear distance on the wall. because we get the dx over L equals m lambda. So x is going to equal m lambda L over d. So kind of the important forms of this, I know that there's lots of equations that I just kind of threw up here on the board. The important ones are the original one, and that came just by doing the geometry, looking at the pairs of waves that are going to come together and destructively interfere. Okay. And then the other one that's useful is this guy, because it doesn't involve the angle at all. It just involves the lengths and the distances. So if you go back and you look at the lab you guys did and the numbers, you probably had a formula that looked a little bit like this. And that's what you were measuring. You're measuring where were those dark spots. Okay. So I know this was now a while ago, because it was like 10 days ago when you were in lab and you did this experiment. But when you did the single slit and you saw the bright, dark, what did you notice about the intensity of the bright spots? Do you remember at all what it looked like?
Are we talking with single slit?
Yeah, with the single slit.
It faded.
Okay, so what do you mean by it faded?
Like this, I guess what you could call the central bright spot was the brightest, and then the next bright spots were faded. They were
Okay.
less bright, less intense.
Okay, so if I was going to say draw a graph here of, let's do intensity, and then this is going to be just the location on the wall, right? You had your brightest in the center. That's what I'm hearing you say, that it was brightest in the middle, and then it got dimmer as we went out.
Yeah.
I mean, obviously the exact shape of this, who knows, but it did something like that.
Yeah.
The rest of you, does that seem right? Does that feel right from what you remember?
Yeah, I remember that.
Okay. I'm gonna see real quick. I know you're just seeing my whiteboard. I'm gonna do a real quick Google search here and just see if we can find a image. See if I can get what I want to see. Oh yeah, here's a good one. Okay, let me change my share here real quick. So let's pull this up. Okay, so here's a picture showing you the double slit pattern and the single slit pattern. And hopefully you kind of remember this. It looks a bit like that. And so here is that single slit pattern doing exactly what Bradley was talking about. The central one is very bright. And as you move further out, they get dimmer. You can see a third one here that's quite dim, right? So there's definitely this oscillation of bright, dark, bright, dark, bright, dark, bright, dark. But also those bright spots are getting dimmer. But what else do you notice about the bright spots as you move further out to the sides?
They decrease in size.
Yeah, they kind of get narrower, right? Like you look at this central one, it's much wider than the next bright spot. And the one after that, it's hard to even see how wide that is because it's so dim. But it definitely appears that it narrowed off. But check this out. What if there was a dark spot right in the middle? And then you look at those widths are actually kind of comparable. And so the reason that that middle one looks like it's so much wider is because there is no centralized dark spot. And this is a difference between the single slit and the double slit. when we did the double slit, we saw that there was that nice regular, here's where all the bright spots are, and it was countable. Um, but this one, it's dark spots we're paying attention to, and there is no zero dark spot. The dead center is not a dark spot. And so that's why it looks like these are narrower. They are narrower, but they're exactly half the distance. Like if you were to look at the dark spot where I've got my little finger pointer right now to this dark spot length, that's going to be twice the distance, or half the distance, I should say, as this dark spot to the one on the other side of the central fringe. So even though it is wider, it's only wider because there is no dark spot in the middle. And this is a big difference between interference and diffraction, right? Diffraction gives us kind of a slightly different thing. Okay, well, it turns out that if we were to look at intensity, let's adjust our graph a little bit to take into account that there are other bright spots that are occurring. Yes, those bright spots are darker, but if you take like this second fringe, not the central one, but the first one that's off to the side, there is a brightest part of it. The part that's in the middle is brightest, and it gets dimmer as we go out until eventually it gets dark and we don't see it anymore. And we see sort of the same thing happen in this centralized fringe. The central fringe, the middle is very bright, and it does get dimmer as we go out. So let's adjust our graph a little bit. Let's go back to the whiteboard here. Let's adjust this so that it's actually matching what we're seeing on the whiteboard. So let me erase those things, and we'll see if we can kind of put better ones on. So here's what I'm going to do. I'm going to mark actually dark spots. Okay, so here's a dark spot. If I go that same distance out, that's going to be another dark spot. Same thing over here. There's going to be a dark spot and another dark spot. And I got room for a third one over here. So those are all dark spots, which means the intensity at those points is going to be 0. Okay, so I'm just going to go ahead and draw dots there. Those are the places where we get destructive interference. Those are the ones that come from this formula right here. So the x's, this x right here would be lambda L over D. This one's going to be 2 lambda L over D, 3 lambda L over D, and so on and so forth. Okay, I'm just letting my m's increase. So then this one would be minus lambda L over D, minus 2 lambda L over D, so on. Okay, so our intensity has to drop to 0. So what we're seeing with that first one is something that does this. Okay, now it's going to get brighter and then drop back down to 0. So we're going to see another little hump, but this hump's not going to be as tall. So it's going to do something like that because it was dimmer than the centralized. It was definitely a symmetric picture, so we're going to see something that does like that. When we go to the third one, we're still going to see another hump, but this hump's going to be even lower than the one before. So again, from symmetry, we get a little lump. And it would actually continue this pattern, but those bumps get lower and lower and lower. They get dimmer and dimmer and dimmer until eventually we don't see anything. So that's probably a little bit more accurate of a graph of what we're seeing when it comes to the intensity of the light. Okay, so then the question is, okay, yay, that's what this intensity looks like, but is there a formula for this? Is there a way that we can actually generate some sort of an equation for that guy? And the answer is most definitely yes.
Right. I have a guess it's going to involve a trig function.
Oh, you think?
Yeah.
The fact that we've got that oscillation definitely should suggest that. The fact that it's never negative, what is that going to suggest to you? What kind of form should show up in that to make that happen? Because if we just had like sine or cosine, obviously sometimes it's going to go negative, right? So what can we do to something to make sure that it's never negative?
Well, absolute value, I guess.
Okay, so we could do an absolute value. That works a lot. What else will make something always be positive? What other kind of basic thing?
Multiply by -1.
Okay, if we multiply by -1, though, if it's positive, then it
Negative
turns negative.
1 to the n.
Okay, so now you're getting into the nice series idea, right? Like where you're like, okay, so let's do some sort of -1 to an n+1 or n. Well, it turns out that it's got a square in it. All right, and so this is what it actually looks like. If we've got I is our intensity, it's going to depend on I naught, and I naught is the maximum intensity. And then we're going to get a sine beta over beta. And that's squared. Now, I still need to tell you what beta is because beta is kind of complicated. But I want you to see why this form is going to do what we want. Okay, so first of all, the sine beta over beta. Sine of beta is going to make it so that it oscillates, right? It's going to go from +1 to -1 and back and forth. By squaring it, it makes it so that it just goes between 1 and 0. So like if you were to draw a graph of sine squared, you're going to see it just oscillate from 1 to 0 to 1 to 0, and it just continues doing that. Okay, by dividing by beta, now beta is going to be a measure of how far we're going this direction. So think about what happens to that. As beta gets bigger, what happens to sine beta over b or over beta?
It's going to go to 0.
It's going to drop to 0. Okay, so that's why we see that maximum intensity dropping off to 0. And then it's all a factor of the maximum intensity. Okay, so that's why this form is going to work. But then the question is, well, what's beta? Okay, well, I'm not going to this to you guys. You can look into the book if you want to see where it comes from. Sorry, here, hold on a second. It's going to pause real quick because my wife just sent me a message on my phone and it says, "Tell them hi, but I'm not in the garage." That just made me laugh. I don't know if who all was here when that happened, but all of a sudden my phone like connected to her Bluetooth in the car and she was talking to you guys from the garage. So anyway, sorry about that. Let me go ahead and get back to this. So the beta, oops, that's funny. I was trying to move my window and I ended up drawing on it. What it equals is actually pi d times the sine of theta over lambda. So these now, the d and the sine of theta, those are the original ones from our slit. So d is the width of the slit, and then theta is off in the direction where we're heading. So we could replace that sine of theta if we wanted to with an x over L. But notice, I mean, this is kind of crazy. We've got a sine of a sine that's being squared. It's actually pretty complicated. To do it, you use these things called phasors, not like Star Trek phasers, but there's a mathematical thing called a phasor. Have you seen those before? The only time you would have seen it is maybe in E&M. So did Kathy ever talk about phasors?
I mean, not that I recall anyway.
I don't remember her mentioning that term before.
Okay. So I'm not going to go into it because I don't want to have to try to get you up to speed on phasors, but they're like vectors. But anyway, so if you use phasors in the derivation of this, you get this formula. But this is what happens when we have light that passes through a slit. We get this sort of form. Now, I want you to think about why you don't just naturally see that. Like, just think about your eye for a second. You've got a slit in your eye that the light passes through. It's the pupil, right? The really dark spot right in the middle. And so there's gonna be diffraction as light passes through that, but you don't see this. You know what I mean? You don't see multiple images of something. You don't see it where there's a really bright one and then it gets darker on either side. Like, we don't see that. So the question is, why don't we see that?
Because our brain is smarter than that.
Okay, so there definitely could be a little bit that your brain compensates for it, just like we were talking about how the image gets flipped over because of the lens, and so our brain then retranslates it to being upright. Or maybe when I see something that I think is upright, maybe it's actually upside down. That's like philosophy now, right? But okay, so here's the deal though. Think about where these are going to happen. Okay, let's think about where those dark spots are going to happen. And let's also think about how this intensity thing drops off to 0 and all that. So let's start with where these are going to occur. So obviously it depends on the wavelength, and that's part of the reason why you don't see this. Because like when you're out and you're looking at the mountains, there's light of all kinds of different wavelengths that are coming through your eye. They're all going to be doing a pattern like this with different, locations of dark spots depending upon what the wavelength is. And they all kind of overlap. So there's that. So we might have a dark spot from one color, but another color is still pretty bright at that point. And so I think that's to the point that Bradley was saying, where your brain is smart enough to just sort of take that into account. But notice what happens when D starts getting smaller. As D starts getting smaller, your X's bigger, meaning these things move further away. And that's part of why our eye doesn't have a problem, is because of the X's. But even better is if D gets bigger. Like, think if D is big compared to the wavelength. So let's even just think about your eye for a second, and let's put some numbers that are appropriate. So light, let's just say we're talking about red light. So we're going to talk about 600 times 10 to the minus 9. That's our lambda. Don't worry about M, because M is just a counting number. So we're just going to look at what's the distance between these, all right? Not which one we're at. So that's the length there. Now, the L is the distance from the pupil to your retina. Okay, now I don't really know how big my eyeball is because I've never pulled it out to play with it. I'm not Newton. I'm not going to be like shoving rulers in there and try to figure out what's going on. But I'm going to guess, what do you think, on the order of an inch? More or less?
Yeah, like
A couple
one.
of centimeters.
Yeah, 1 to 2 centimeters.
Okay, so how about we'll just go with a couple of centimeters. Let's just go with 2. And we'll do centimeters. So that's times 10 to the what, -2. Okay, so that's our L. So we got lambda and we got our L. And then we need D, the diameter of your pupil. Now, this is going to change. Like you guys know about when your pupils get dilated when it's bright or dark, and then they get constricted when it's bright, right? So our eyes adjust that to basically protect our vision. But even at its smallest, I mean, definitely no smaller than millimeters. So let's just go with millimeters as our size of our pupil. Okay, so we'll go 1 times 10 to the -3. Okay, so if you were to do the numbers on this, we're going to get 1200 times 10 to the -8, which is 1.2 times 10 to the -11. Ballpark. Don't worry too much about the 1.2. All right. And even if you don't like the 10 to the -11, you might go, oh, well, maybe it's really 10 to the -10. Okay, cool. Go for it. So think about what that means. That means that this distance right here, I mean, that's smaller than nanometers. Going to appear, it's really going to look as if it's a point source. So that's really why we don't have that problem with our eyes, that we're not that we're not running into this refraction issue, or sorry, diffraction issue, just because the sizes are such that gap is so big compared to the wavelength that we don't see this effect. Do you remember what size your gap was when you were doing this in lab?
0.04 millimeters.
Okay,
Yeah.
so it was on the order of 10 to the -5 ish meters.
Yeah.
Okay, so compare that to the number that I just put up here, 10 to the -3. I mean, you're talking about 1/100th. And so you guys know very well that you go a couple of order of magnitude and you can get a very different kind of picture, right? And think about the distance that you were traveling, the L, from your slit to the screen that you were projecting on. Much bigger than an eye, which allows for much bigger separation, because what if that screen was right here? Now we're seeing a much shorter X. And so it just turns out that with our eye, we don't run into that problem because of the geometry. We're close enough. The retina screen is close enough. And the gap that it's going through is big enough that it tends not to be an issue. All right, well, it is kind of cool, I think, that this is the pattern that we see even if we're going through a single slit. It's just we don't normally notice it because the numbers involved are such that it's not a thing. And it's usually because D is so big compared to your wavelength that it makes that X so small, as if it didn't even happen. But you see something very similar with like physical waves. If you were to look at build like a little harbor where you've got just an opening to the ocean like this, you'll still see the same thing where you'll get the intensity patterns, kind of like what we drawn here. And so there are going to be places inside where you get greatest wave intensity, which kind of makes sense, right? Imagine that that this is the little hole and the breakwater, and then we've got our pier. You should expect that there's going to be a lot of wave activity right here, right? Because all that energy is coming in. But what's surprising is that there's also going to be a place of higher activity out on the sides. That would correspond to those. And so if you were going to be designing a marina, you got to take that into account, which is why there isn't usually just one little gap. They'll have other things in here to help break up the power of the waves that make it through. But diffraction still happens out there with physical waves. It's not just light waves. All right, so real quick, some places where we actually use diffraction, because diffraction is a thing that we apply in the real world. We make what are called diffraction gratings. And you think about a grate, like a sewer grate, you probably think of, a piece of metal with slats on it. Let me turn off so you guys can see me. So you think about like a grate. It's usually like rectangular with a bunch of slats, right? Well, a diffraction grating is actually kind of the same idea, where what we're going to do is we're going to create a whole bunch of slits. So not only are we going to get diffraction, but we're also going to get the interference. Actually, real quick, while we're on that, come back to, let me share that picture again that had the, I got to find it, hold on a second. The picture of the single slit. There we go, let me share this now. Right, so come back to this one where we have the single slit and the double slit. I want you to notice that even in the double slit pattern, we're seeing the single slit diffraction. Right, look at this big central bright spot. We still see this central bright spot. It's just broken up into smaller bright spots. So that bigger pattern of big, bright, not as bright, not as bright, so on, that's coming from the fact that we've got light passing through slits. So that's diffraction. And then the individual dots within that, that's coming from the interference from the double slit. So you can actually have both of them combined. And so imagine now we put on a third slit or a fourth slit or a fifth slit, or there's 1,000 slits. It's going to create a very distinctive pattern. That's a combination of diffraction and interference. And that's what diffraction gratings do. So I'm going to actually see, let's see what Bing has to say if we go to diffraction grating patterns.
I have a quick question for you.
Yeah, go for it.
You know how, at least with light waves, there's always the source, right?
Uh-huh.
Well, I was thinking about the ocean and their waves themselves. Where is considered the origin of where these waves start?
Which ones?
I
And I don't mean that to be flippant. It's just there are a bunch of different kinds of waves
okay.
that are out there in the ocean. So, for example, tidal waves, and I don't mean tsunamis. I mean literally formed by the tides. Those are, I mean, basically the source of those is the moon and the sun, causing a bulge in the water that the earth is then rotating under. So it's not so much that there's a wave, but it's the rotation of the earth that's making the earth go into, like, roll into the high spot and then into the low spot, high and low and high and low. You remember in trig, that sinusoidal stuff comes from rotation just as well as anything else, right?
Yeah.
So like tidal waves, the tides going up and down, those are really due to rotation, not actual formation of a wave. But where you will get waves, and these are more the waves that you think of when you think waves on the ocean, a lot of those are wind created. As the wind is blowing over, it's creating the waves, because you'll get some pressure differential due to that, and you'll also get some like physical buildup as the wind is blowing the surface water here up, and now next thing you know, oh, we've got a crest, and then gravity pulls it down, and then wind blows some more up and down and all that. So a lot of those are actually formed kind of close to the shore, but you can also get the like really big swells, and what I mean by that, because if you've not spent time on the ocean, you may not know what that's like, but that's where like you're just out in the middle of nowhere, and the surface isn't doing the little wavy thing like you're used to seeing on the shore, but you just always you go up, and then you get dropped down, and then you go up, and you just drop down, and so it's not a like wave pushing you through. But those often are also created by winds, but then they build over time. So it's not like there's the thing in the water that's moving and making the wave. But most of them are due to wind effects, atmospheric effects. Anyway, so yeah, waves are cool.
Sorry, I couldn't help myself.
No, that's all good. And you know me, I'll talk about waves all day long. Okay, well, I didn't really find any good pictures. Like I kind of found one. I don't know if you guys saw it. Let me pull it back up. But like, here's a pattern that you can get when you pass light through a diffraction grating. Now, this one's not going to be one where you've got a whole bunch of like, say, parallel slits. This is going to be one that's got a bunch of like crisscrosses. And as the light goes through it, you actually think of this as like a two-dimensional extension of what you saw in 1D, right? Like just look across here and you can see there's the really bright central spot, and then there are the alternating bright darks, but those brights are getting dimmer as you go away. But this one, if you look at the intensity, the light intensity, it doesn't follow the pattern we saw for just regular old diffraction, right? Because the other one, every succeeding maximum got dimmer, but we don't see that. It's got bright, then dimmer, then brighter, then dimmer, then brighter. Well, that's because there's now more interference happening from more than just the two openings. And you can get some really complicated patterns depending upon how you set up the diffraction grating. Okay, so where this is used is places like CDs. I know I'm now totally dating myself because nobody uses CDs anymore, but you guys know about CDs.
No, that makes a lot of sense now that you say it, because there's that. It's usually red laser inside the CD player.
Okay, so there is a laser in the CD player. I'm trying to. You would think that they'd have a picture of a CD here where we're talking about diffraction gratings. Let's see. Let's go with the CD compact disc. Anyway, so a laser shines against the compact disc, and even if you don't, oh yeah, here we go, beautiful. That's what I wanted to see. Like even if we're not shining a laser on it, when you look at it, you see all the different colors of the rainbow, right? And as you kind of tilt it around, you'll see the various colors. Well, that's obviously due to refraction. That's coming from diffraction, but that really, it has a bunch of, for a lack of a better way, a bunch of grooves in it. And as the light shines on it, It's a diffraction grating, and it produces a pattern. So then the computer, or whatever you want to call it, reads that pattern and translates it to, oh, you're supposed to hear this sound. All right. And so as it's spinning around, it's passing over the laser, and the laser is hitting against all those different things, and it's creating a pattern of signals that then gets translated into the music that you hear. So anything that's got an optical disk drive does that kind of thing. All right, now another place that this happens is when you're at the grocery store. Think about when you're checking out, right? And they take that box of Cheerios and they go over the, little thing, and it go boop, and it pops up Cheerios, $3.99. I don't know if you've ever wondered how it does that, but that UPC code, right? The UPC, the Universal Product Code, the black and white stripes. I wonder if I've got one. Oh yeah, right here. Right? So that series of black and white stripes, that acts as a diffraction grating. Because think about if we shine a laser at it, and there are lasers in there. Next time you're at the shopping, at the grocery store, right? You're at Rayleigh's or something. When you're checking out, you'll see it. You'll see like all kinds of beams that are cutting through there. They do that just so that it makes it a little bit easier. You don't have to line it up exactly, but it's going to reflect differently off of the white and off of the black, because I like the difference between white and black, honestly, is absorption versus reflection. If something looks white to you, it's because it's reflecting all the visible light, or at least almost all of it. So your brain reads it as light. Excuse me. And then it's going to look black if everything's getting absorbed. Okay, so when you see something black, it's all the visible light is getting absorbed, or at least enough of it for your brain to interpret it as black. Okay, well, as the lasers bounce off, it's going to bounce off the white and get absorbed by the black, but it's going to create a very specific pattern. Okay, well, now insert computer. Computer reads that pattern, translate that, and goes, oh, that was Cheerios. Right, and then somewhere in their system it says, okay, so Cheerios cost $3.99, so let's put $3.99. But really what it's reading is, it's reading it as Cheerios. So like if you had a UPC reader, and they probably make them, I don't really see the point, but if you were to have a UPC reader and you were just to go into Rayleigh's and start scanning things, you wouldn't necessarily get the price, because the price is set by the people that are selling it, but you would at least be able to read off the numbers. And if you had a database of what the different numbers were for different things, it would come up as Cheerios, right? But that's another place where we make use of diffraction patterns. Kind of trippy, kind of crazy, but I'll tell you what, it's made shopping a lot faster and a lot easier. You guys are probably not old enough to remember this, but back in the day, they had to manually type in everything. Oh man, it took forever. It took forever to check out. Plus, you're there with your mom, and you're like, I just want to get home and watch Super Friends. Come on, let's get home with this. Anyway. Okay, so diffraction's a real thing, and we make use of it even out there in the real world. But there's another kind of consequence to this that you may not actually think about, but this gets to what we call resolution. And I was kind of hinting at this before, but let's say you're looking at the mountainside. When it's kind of far away, when you're looking kind of far away, like let's say you're standing there at like, Pope Beach or something, and you're looking out across the lake, you can tell that there's a place that's forested, that has trees, but you can't specifically pick out individual trees. But then if you look closer, right, so you just look down towards Baldwin or something, you're going to start getting close enough where you can discern individual trees. And that's what resolution is. So when we talk about resolution, it's the ability to resolve individual images instead of the blanket, yeah, there's trees there. Oh, there is a specific tree there. Okay, so that's resolution. And resolution actually has everything to do with diffraction. And let me show you. So pull up white. Let me clear all this stuff because it's gotten a bit messy. But let's say we've got two different trees, and these trees are going to be creating diffraction patterns as the light comes through our eye. Okay, so here's tree number one. We'll make it blue. I'm only going to have individual colors so that we can kind of see their diffraction patterns a little bit better. But obviously, I'm going to assume they're actually kind of the same color. But anyway, so there's that tree. Now, here's our eye. So we're going to have the pupil in our eye that the light's passing through. And then we're going to have our retina. Okay, so retina, pupil. Obviously, there's more to the eye, but this is the only part that we care about. Now, think about the light that's coming from that blue tree. It's going to pass through our retina, or sorry, pupil, and it's going to create a diffraction pattern on the retina. Okay, so let's just say that that's what we're seeing. So here's our maximum intensity. And so our eye is going to see that tree as being at this spot. All right, now let's say that there's a second tree over here. We'll make it red. Same thing's going to happen, but it's going to produce another pattern over here. And they're offset just because of the angles, right? If you think about the angle from the tree through our eye, they're going to do that kind of thing. So if they're separated by enough distance, we're clearly going to see two images because, like I said, the blue one's going to appear to be at this mark. The red one's going to appear to be here. Our brain's going to be able to see the difference. And yeah, there's a bunch of overlap of these patterns, but you saw how quickly it dimmed down, right? Like beyond that second, you really don't see anything, right? So pretty much once you hit that first dark spot, the rest of it we don't really care about. So in this sort of circumstance, you're going to see two completely different pictures, two different trees. But let's bring those trees closer to each other. So we're going to do the same thing. So we'll have the slit for our pupil, we'll have our retina. But this time, let's bring the trees a little bit closer. So closer to each other, I should say. So let's have our red one be here. If I kind of follow that through, I'm going to get my diffraction pattern that looks like this. All right, so that's where we think the red one is. But then if we've got our blue one much closer, and we follow it through, we're going to see this kind of picture. Okay, so here the red and the blue where we think those two things are. And you can see that now these things are really starting to interfere with each other. And if you were to put those waves together, so I know I've got them different colored, but suppose they're not different colored and we're just going to literally add those waves together. Think about what you're going to see. You're going to kind of come up to this brighter spot, but then instead of decreasing right away, you're going to continue to increase because we're adding the reds and the blues. So maybe we get a little bit of a blobby thing like this, and then down. So this is actually the net result of putting those two together, as opposed to the first example. If I were to put those together, we're going to see something that looks like that. Yeah, there's going to be some stuff in the middle, but it doesn't even rise close to the peaks. So think about what our brain's going to be able to do here. It's going to look at this one on the left and go, oh, there are two objects. It looks like there are two distinct objects. This one, our brain's going to go, oh, there's only one object. We're not going to be able to tell that there are two different trees, right? And this is exactly what I'm getting at, where if you look far enough away, it's something far enough away, you can tell that there are trees because we know what that looks like, but we don't have the ability to see individual ones. So the question is, all right, well, how far apart do these things have to be for us to actually be able to see two distinct objects, or for our brain to be able to see it? And this is pretty much how it's been determined, that you're going to be able to see two different things. So you can resolve the two images when the intensity, not the intensity, the maximum intensity of one. So the peak of max intensity for one of them is at least as far away from the other as the first dark spot. So if we come back and we look at like this image where they're kind of separated, the reason that we can resolve the two is because the first dark spot is right here for the red, right? And you notice that our max intensity is quite a ways from it. And then in this circumstance, I've got them pretty close to each other, but there's the first dark spot, and our max intensity is pretty much right there. So this is at the verge of being okay. But that's what I mean, that it's got to be at least as far away from the other one as the very first dark spot. Okay, so if we define it that way, we can actually figure out exactly what kind of angles we need, what kind of separation we need to see the two different images. Right? Because we've got our relationship between the location of that dark spot and the angle, right? And so this was actually studied, and they came up with what's called Rayleigh's criteria. Now, the thing about Rayleigh's criteria is a little bit different. Let me just erase this stuff up here. Get rid of the trees. Because Rayleigh's criteria is all about having a circular aperture. And what that means, circular aperture, an aperture is just an opening for light. So it's the gap in the screen, or it's your pupil. Okay, that's a circular aperture. Or an aperture, but a circular one is actually a circle. And if you look at something that's round, so we've got multiple dimensions, it changes things a little bit in the math. So Rayleigh's criteria is going to take that into account. But it's called Rayleigh, not like the grocery store Rayleigh, but I get maybe Raleigh's or Rayleigh's criteria. And if you run the numbers on it, you find out that the two objects are just barely resolvable, or very first time that they're resolvable. I'm just going to say here, are first resolvable. I don't even know if that's a word, but we're going to go with it. When the angle between them, theta, is equal to 1.22 lambda over d. And obviously lambda is the wavelength. D, this is the diameter of the circular aperture. So in the context of what we're talking about, that's the pupil. But if we're talking about taking pictures using a camera or something, it's the opening on your lens or whatever. So that's the diameter of the circular aperture. So in the case of the pupil, because it is a circle, right? That would be your D. And then the theta is the angle separation between the two objects. Okay, so that's why remember this other case, the trees were much closer to each other. If I were to put in we didn't actually have that, but you'll notice that this is now a smaller theta. And if that theta gets too small, we can't see it anymore. And this is the cutoff. This is like the bare minimum. Now, obviously, different people have different abilities, and it's not going to be exactly that for everyone, but this is real life. Like, here's another good example. Think about when you drive your car or you're riding in a car and you see cars coming towards you with headlights on. When they're far away, you can't tell that there are two headlights. You just can't. I mean, you can tell that there are lights coming towards you, but you don't know that there are two of them. But eventually they get close enough that you can see two different headlights. That's exactly the same thing, right? Think about those two headlights. They're separated by a specific distance because they're on either side of the car. And so as they come closer to you, the angle to those two spreads out. And eventually it gets wide enough that you reach Rayleigh's criteria and you go, oh, cool, there are two headlights. All right, so this is so real in so many places that we actually see this. And they actually make use of this in a specific kind of art. Do you guys know about Pointillism? You heard of that?
I have not.
Okay.
Nope.
Okay. So Pointillism, this is actually one of my favorite kinds of art because it's really kind of cool. Let me pull up let me share my screen here. And I'm trying to remember the really famous one. I'll probably remember it here at some point. But here are some examples of pointillism. So take a picture or take a look at like this picture here of the sunset over the lake or whatever. If you look really,
mosaic.
Yeah, if you look really closely, like there's a kind of a good zoom in one here, it's actually made up of just dots. And that's why it's called pointillism, because you're making points of paint together. And if you zoom in really close, you can actually see the points. But when you move further away, they're harder and harder to tell. So here are some really good examples of different ones at different locations. Like look at this one with the farmhouse. You can really see the points. Take a look at this one with the, looks like a magician. Can you actually see the dots? Yeah, I don't know about you, but I can tell it's a little bit kind of fuzzy-ish, but I can't actually discern the dots. And probably the most famous one, it's this guy, this one up here. I don't remember who that is. I want to say Surratt, I don't know. But it's called like Weekend at the Park or something like that. You remember when the Bernie meme thing started going on? And Bernie started showing up everywhere wearing his mittens and stuff. I remember seeing one. It was like Bernie at the park, and so they put this one. But if you've ever seen Ferris Bueller's Day Off, that movie, if you haven't seen it, you should check it out. It's a pretty good 80s movie. But they go to an art museum, and one of the characters is just like looking at this art, and they alternate shots of looking at the face of the dude. His name's Cameron, and then showing the painting. And they then zoom in on his face, they zoom in on the painting, they zoom in on his face, they zoom in on the painting, and you really get to see the anyway, that effect. But anyway, oh yeah, it's Surratt. There you go. Jacques Surratt. He did a lot of them. So this is in Chicago at the Met. But anyway, my point is that this is making use of that same deal. When you are far away from this painting, your eyes do not have the ability to discern the individual dots. They can't resolve them because their angle is so small that it's under Rayleigh's criteria. But as you move closer, the angle gets bigger because you've gotten closer, right? Yeah, angle gets bigger, that you're eventually able to resolve it and see the individual dots. So it's pretty cool. I'm a big fan of it. I had the opportunity to go to Paris a few years ago and went to some of the art museums, and I found an area in one of them that just had pointillism like crazy. And yeah, that was by far my favorite part. Anyway, I'll go ahead and stop that. So these effects have been known. Like, do you think Surratt had studied his physics? Do you
No.
think he had looked at phasers and run the math on the intensity of the light and figured out, oh, with ray, like I would bet actually some of this was even after his time. I'm not really sure when he was around, but he didn't do that. He didn't think about that, but he knew it was there. He knew that it existed, and we now can explain it. We can run the numbers on it. We can do the math behind it to show why it is how it is. All right, so basically all this stuff comes down to diffraction, or it's the fact that light is a wave, and even when it just passes through one slit, will do the same thing. Other places that this is used is like holography. You guys know about holograms. If you've got a credit card, probably has one on it. I know that I think our passports have them. Some of our IDs have them, depending on the state. But you know
Money.
what I'm talking about, right? Yeah, actually, some money has them, has holograms. Okay, so holograms are actually created using diffraction. They use diffraction and mirrors and stuff to create multiple images that give it that three-dimensional feel. But you notice how the holograms are always kind of rainbowy colored. Well, that's a result of the diffraction, right? Only US money I know that has that are hundreds, and I don't usually see hundreds very much because I'm poor. But I'm actually curious. I got my passport right here. I'm pretty sure there's a Yeah, it's got an overlay and hologram. You can't really see it. I'm gonna cover the important information. Nah, I'm gonna show my passport on YouTube. Never mind. I'm smarter than that. Anyway, I don't know where I was going with that. But holograms are another place where we use diffraction. Anyway, so kind of cool. All kinds of weird optical effects out there that we can explain. And it really comes down to the fact that light is a wave, right? These last couple of chapters should convince you that light is absolutely a wave. Even though the first couple of chapters, we treated them as particles, as rays. And the fact that it's both feels weird sometimes, but what you're gonna learn real fast is that everything has this. Everything has a wave particle duality. Electrons have it. You have it. Your dog has it. Your computer has it. Lithopane. Victor, I don't know what lithopane is. What is lithopane? I can Google it. Thank you.
It's hard to explain, but then
Okay.
it's of everything.
So, all right, let me just. Okay, so it's an etched or molded artwork in very thin, translucent porcelain that can be seen clearly only when backlit with a light source. All right, I'm going to tell you I don't know yet. Let me look into it a little bit, because since I don't know what it is and I don't know that I've ever seen it, I don't know that I can necessarily describe why you see what you see. So let me look into it a little bit, and I'll get back to you on that.
I have a question for you.
Sure.
So suppose your pupils increase in radius, and so
Yep.
they're bigger than normal, and you look up at, say, a straight light, and suppose they do not, decrease in radius to, do what they normally do. They just stay the same size. Why is it that when that happens, you see that big orb around it of light?
Oh, I don't know. That I don't know. Well, because kind of what I thought you were going with was going to be, how does that affect your resolution and everything? I do know, like, if you've ever gone to the eye doctor and they dilate your pupils, right? They put some medicine in your eye to make it so that your pupils get really big, so they can look in behind them, and they stay that way. It's actually really hard to do things like read, drive, because everything looks kind of weird. And part of that is because your resolution gets messed up, right? You've now increased your D considerably, which means you're changing the angle for resolution. But the halo, I'm not really sure why you would be seeing the halo around the street lamps. I think you also have this issue just like at night in general, right? Like, yeah, I'm not really sure. I don't have an answer for that one. You guys are stumping me. I don't like this. This is almost as bad as Diffie Q's yesterday. No, I'm kidding. Nothing can be as bad as Diffie Q's yesterday. I was so off my game. Anyway. All right, so moral of the story is light has really cool properties, either wave or particleness. And because it's both, we see it manifests itself as both. But everything we see can really be described using just a few rules. Like, think about it. How many actual rules, laws, whatever, have we talked about in optics?
4.
That's probably pretty close, right? We've got just, okay, reflections. We know the angle of reflection is equal to the angle of. We've got refraction, so Snell's law. all of that determined everything with the lenses. So even when you go to, well, but we've got like 1 over DO plus 1 over DI equals 1 over F. No, that came from reflection and refraction, right? I think you could probably throw interference in there, which that's really just a consequence of waves, but it manifests itself in a bunch of different ways, right? So that's where we get the like the interference from the multiple slits, the thin films, diffraction, like all of that comes from just the wave nature and interference of waves. I mean, that might be it. You know, because even other things like when polarization and Brewster's angle, well, that has to deal with refraction and reflection, or, you know, any of that. So we don't need a lot to be able to explain light. And I think that's another reason I really like optics, is that not only do you get to see all these cool effects and get to describe all these cool effects, but you can explain them with just a very little bit of stuff, you know, which I think is cool. All right, so we are done with optics. We are now ready to move on to the next section, which is the modern physics. We're going to get into the really kind of.
I'm stoked. I'm stoked.
So Ralph, what's the FRFR mean?
For real, for real?
Oh, okay, thank you. Remember, old man. Well, yes, I hang out with you guys all the time. I don't know. But yeah, so you think about this class, just the first few chapters are about optics, but it does lend itself really well into the modern physics, leading into the modern physics. Because like I said, we're going to find out that even things like electrons have wave-like properties. And a lot of what we talked about in optics, specifically with the last couple of chapters here that have to deal with the wave-like properties of light, we're going to see that the same thing happens with matter. Spoiler alert, but we're going to find this out eventually, because a lot of times people go, nah, there's no way that my finger has wave-like properties. And it does. It's just the wavelength is so incredibly small that you can't see that it's a wave. Right. And so that's what we're going to see, that these wavelengths are such that they're so tiny that you can't even tell the difference. And then we're actually going to see how, when we describe matter as waves, how we can actually use that definition to show particles and the particleness of waves. So it all kind of wraps together, which is kind of nice, even though it's a real trippy kind of thing. Anyway, so I don't really feel like diving in yet to the modern physics. So we're going to go ahead and call it a day. Let me go ahead and stop our recording here.